Dankeschön. Ja, auch von mir herzlich willkommen. Mein Teil wieder auf Deutsch. Auch nochmal das Zeichen für unsere Schülerinnen und Schüler. Ihr könnt nachher fragen, in welcher Sprache es euch immer besser passt. Das neue Jahr ist erst am 12. Tag und es ist schon ganz schön viel passiert. Es scheint dem alten Jahr so ein bisschen den Rang ablaufen zu wollen, aber wir konzentrieren uns heute mal auf die Wissenschaft. Und wann, wenn nicht in diesem Jahr, ist uns klar, dass große Datenmengen gebraucht wurden, um möglichst schnell zu reagieren auf ein Virus wie der jetzt hoffentlich in den nächsten Wochen mit Impfungen bekämpft werden soll. Sind ganz glücklich, natürlich Professor Fuchs hier zu haben, kriegen noch mal einen anderen Aspekt auf den Umgang mit Big Data. Professor Fuchs, der heute in Österreich ist und sonst auch oft in New York, also auch nochmal Grüße an die anderen Schulen an der Ostküste. Wir haben immer mehr Participants und diesmal ist es sogar so, dass hinter manchen Einwahlen sich eine ganze Klasse noch verbirgt, sodass also immer noch so mal 20 dazukommen. Vielen, vielen Dank für euch, dass ihr uns hier besucht zu unserer Lecture Series. Wir sind natürlich froh, dass sie so gut ankommt bei euch. Wir sind dankbar dem Hasso-Plattner-Institut und ich kann schon ankündigen, die nächste wird für unsere Abiturienten erst nach dem schriftlichen Abitur sein, nämlich am 25. Februar. Dann wird Professor Meinl kommen, der Head of HPI. Und jetzt aber zu Professor Fuchs und ich übergebe an Joanne Halpern aus New York, die meisten, die hier immer, die fleißigen Teilnehmer auch schon kennen und Dr. Halpern wird Professor Fuchs vorstellen.
Okay, thank you, Katrin. And I'll go back to English. So first, I'd like to thank Katrin Rösche, whom you just met, Carol Hink, Jenny Jungblut, Heike Kriege, Katrin Wöppner, and all of your team from the German International School at Silicon Valley for this great collaboration and organization that you've done. Professor Thomas Fuchs, who you will hear from soon, is a scientist in the groundbreaking field of computational pathology. His research focuses on the use of artificial intelligence to analyze images of tissue samples to identify disease, recommend treatment, and to predict outcomes. In October 2020, we were honored that he became co-director of the Hasso-Plattner-Institut for Digital Health at Mount Sinai in New York City. He's also Dean of Artificial Intelligence and Human Health and Professor of Computational Pathology and Computer Science at the Icahn School of Medicine at Mount Sinai. In this role, he's leading the next generation of scientists and clinicians to use artificial intelligence and machine learning to develop novel diagnostics and treatments for acute and chronic disease. But before he got to Mount Sinai, he was the director of the Warren Alpert Center for Digital and Computational Pathology at Memorial Sloan Kettering Cancer Center, which is also in New York City. And he was an associate professor at Weill Cornell Graduate School for Medical Sciences. At Sloan Kettering, he led a laboratory that focused on computational pathology and medical machine learning. He also co-founded Page AI. So he's also an entrepreneur, and that he founded in 2017 and led its initial growth to become the leading AI company in pathology. He's a former technologist at NASA's Jet Propulsion Laboratory and a visiting scientist at the California Institute of Technology. Thomas, it's an honor to have you join us today, and the floor is yours.
Thank you so much for the kind introduction. That's really much too nice. I hope you can hear me well. It's an honor to talk to all of you, and I hope I'm going to tell you something interesting about artificial intelligence and especially its impact on healthcare. Let me share the screen. So, does that work? Can you see the slides?
Yep.
So thank you so much for the introduction. As you can hear, I'm originally from Austria, so for the questions afterwards, I'm happy to answer them in English or in German. It's also great to hear that so many schools are dialing in. We actually visited the one in Westchester once. It's a beautiful area, and I know that German international schools are a fabulous network with excellent education. Good. So here's the disclosure slide. As Joanne mentioned, we started Spinout, a startup a few years ago called PAGE, that stands for Pathology Artificial Intelligence Guidance Engine, and that's a startup in the space of pathology and AI. Good. So what is AI? When we talk about AI, very often for a lot of people, images of robots or Terminators come to mind. And if you actually recognize my accent, I'm originally from the same town as Arnold Schwarzenegger, so there's certainly an overlap there. But practically, of course, AI these days has nothing to do with these movies and even with robotics. So machine learning already is omnipresent in our daily lives. We have knowledge systems that inform all kinds of systems, from your Alexa devices, from your smart speakers. In some areas, you have already self-driving cars or self-driving assist systems. In medicine, there are areas like pathology or radiology where these systems are used to detect cancer. And then, of course, there are also nefarious uses of AI, especially if it goes to surveillance and also in cybercrime, but there's cybersecurity to protect from that. Joan mentioned my past at NASA. There, for example, we use these systems for space exploration, for flyby missions at asteroids to, for example, to detect areas of interest or to make sure the Mars rover doesn't get stuck in sand. Other areas are face recognition. These are very classic machine learning systems already in each of your cell phones or cameras, voice recognition, fraud detection, and so forth. In medicine and in healthcare, there's also a plethora of applications. In the genomic side, you're analyzing, for example, biomarkers. You have approaches where you try to predict the survival of patients. In connectomics, you look at the distribution of the synapses and dendrites and the connections in your brain, while in the disciplines below, you actually look at medical images to do similar things you would do on the Mars rover or for self-driving cars, detect interesting areas, classify them, and so forth. So the way we approach all these problems in practice is machine learning. So machine learning is that field that drives all of these applications these days. And practically, there's a huge overlap between machine learning and artificial intelligence. So nearly everything you see these days, if somebody says AI, practically what you see inside are machine learning algorithms and machine learning systems. They're very old-fashioned AI systems that, for example, are based on rules and so forth, which would not be machine learning, but everything else is machine learning. In addition, to make these systems work, there's, of course, a lot of engineering around. So you're interested in parallel computing, in data curation, databases, optimization, and all these areas. So on a super high level, machine learning works as follows. So you start with a huge set of data that could be, for example, images, and then you use your machine learning magic, and out comes actionable insight. So the data could be your voice, for example, or examples of voice. Then the machine learning magic could be a natural language processing algorithm that detects specific phrases, and the output could be, for example, the selections of your song in your smart speaker. If you want to have a little more fine-grained insight, practically there are classification approaches. So these are supervised learning approaches with discrete labels. So there, for example, you want to predict, does a patient have cancer or no cancer? So yes, no, for example, or multiple categories. On the other hand, regression is for continuous values. For example, if you want to predict stock market ticker or the survival of a patient. And then on the unsupervised side, in clustering, you, for example, try to find subgroups. Let's say you have pictures of, let's say, insects, millions of insects, and you try to find new subgroups. Or again, in cancer research, you try to find subgroups of cancer that behave differently. So here's a very simple example how these systems work for images. So as you know, images in practice are numbers. When you take a picture with your cell phone, then each image pixel is a value for red, green, and blue. And out of these three numbers, all the colors are mixed. And you have millions of these pixels in an image. So that defines your metrics for your image. So these are the numbers which are the input. What you do then is, for example, you do image feature extraction and then build a classifier based on that with the labels. So in this case, we wanted to build a system that can differentiate indoor images from outdoor images. And you show the system hundreds or thousands of images of indoor scenes and outdoor scenes. And then based on the correlations of these pixels, the system learns how an indoor and outdoor image looks like. For example, an outdoor image has very likely blue pixels at the top and green pixels at the bottom. That's of course too trivial. Practically, these systems can check millions of these comparisons. And then you end up with a trained classifier, and that's your smart system. That's then something you can use in your device or in practice. And then if you get a new image at the bottom, a test time, you take that new picture. The picture again is split up into the different colors and values for these. The same features are extracted. And then you use the system you trained before to predict if you see an indoor or in this case an outdoor scene. So that's very simple. Today, most of these systems use a specific machine learning algorithm called a neural network. Neural networks are loosely designed after what people thought and think the human brain looks like or works like. Originally, these systems come from the 50s and 60s, but it's only recently in the last 10 years that we learned how to optimize these systems at very large scale and very deep networks. And these are then deep neural networks. So the input on the left, you would have, for example, the pixel values as before, red, green, and blue for all of these. And then these neurons are connected with each other. And you have weights on these connections. And when you have the pixel values at the beginning, you propagate these weights through the system, and at the end you have an output, for example, outdoor or indoor scene. If you have an indoor image and the system at the end thinks it's an outdoor image, which will be the case at the beginning very often because it's random, then you can calculate an error. So you say it's wrong. And then you back propagate that error through that system again and update all the weights. And that's how the system learns. And you do that over and over and over again. So the connections that implicitly model, for example, that sky should be blue and grass green, and if there's a lot of sky and green grass, then it's an outdoor image, are then trained in that system. What you see here is a very simple network with 4 hidden layers, but modern state-of-the-art networks have 100 layers or even more and can have millions or even billions of these parameters. So these are very high complex systems. Still a fraction of the connection our brains have. So we are by far not at the scale of our brains, but we can build these systems these days at very large scale so they can learn meaningful models of reality. Here again is an example. So what you see in the left is, for example, an image from microscopy, from cancer research, and you want to find the outer layers of these cells in blue on the right. And what you do is you have layers of these networks. A variant of these deep neural networks are convolutional neural networks. There you learn filters over these images, but it's more or less the same as I showed you before. And based on that, you learn the output. Good. So let's take a look how that works in clinical practice today. And I'll show you an example of pathology because first of all, it's the main topic of my research group, and second of all, it's something nearly all of us will have to do in one or the other way in our lives. So how does pathology work today? So suppose you have a mole, for example, or some other tissue that's cut out. Then the pathologists cut these in small pieces, and they're put in these paraffin boxes. They're embedded in paraffin with the bags, and then from these blocks they can cut off very thin slices, and these slices are put on microscope slides, and then they are stained for all kinds of proteins and genes of interest. And you end up with these colorful collections of slides. And it's done, a lot of these are done. So what you see here is the workload at Memorial Sloan Kettering Cancer Center. That's the world's leading cancer center in New York City. And there, each of these folders contains dozens of these slides for every patient. And the whole stack is the workload of just a single week. And then a human looks at these slides. So to that end, pathology has not changed in 150 years. So when Virchow in Berlin actually invented these stains for these slides, that was more or less done the same way. And if a human does that, it can be very subjective. So for example, if you're tired, or you have to look at hundreds of these, then of course humans make errors. And then these slides are stored in these vast archives, and it's really a pristine example of dark data. Memorial Sloan Kettering has 25 million of these, but each large hospital in the world has these. And only in recent years, the scanners became good enough that you can digitize them, so you can take pictures like with your cell phone, and you end up with these very, very large images. So what you see here is, it's actually a personal example. So that's a mole, one of my moles that was cut out. So that's, most of us will have cut out several of these during our lifetimes, and usually they're of course benign, but doctors check if they are cancers or not, and that's done under the microscope. These images can be very large, 150 pixels times 100,000 pixels. So one of these slides can hold all your holiday snaps. If you zoom in, you see the layers of the skin. If you zoom further, you see different structures of the tissue, like vessels. And at the highest resolution, you see cells and cell nuclei. And you are interested in detecting cancerous cells, classifying them, grading them, and helping the pathologist with the diagnosis. So why should you care about pathology? So what you see on the left are screening technologies like radiology, like dermoscopy, so dermatology, skin, for example, or ultrasound, or blood tests, and so forth. So in all these cases, if a doctor finds something suspicious, they have to cut out the tissue, put it on a microscope slide, and then a pathologist looks at it in the center here. And everything else that follows afterwards is based on the diagnosis of the pathologist. For example, the decision if you should be treated, and treated with what drugs, or what strategy, all genetic sequencing, or all pharma studies, all insurance claims, all of the research, everything is based on a human looking at these slides and more or less estimating if that patient has cancer or not, and what kind. So if we can build AI that helps pathologists to be more reproducible and more robust, then everything else that follows in the medical edifice would benefit from such a system. In addition, pathologists are under enormous stress, so the number of cancer cases goes up worldwide, and the number of pathologists goes down, and also the complexity of the cases goes up. And to that end, while I speak a lot about cancer, practically that's every time some tissue is actually taken. For example, if you have a gastroscopy or a colonoscopy, or again in skin, each and every time. Good. Computational pathology to the rescue. So that's the field we are talking about, where we use AI in all kinds of areas. My lab works in 3 areas. One is the diagnostic one. So here we try to build AI systems that help pathologists to do what they already do, but faster, better, and more reproducible. The second area is the prognostic area. There we try to develop systems that help pathologists to do things they cannot do. For example, based on these images, predict if a patient would benefit from a given therapy or not, or how long they would survive, or if, for example, there's a genetic mutation that could be targeted. And all of that is underpinned by a lot of work in machine learning and AI systems. So we build database systems that pull data from all kinds of clinical databases. We build large compute clusters I will talk about to train these models at scale. We build a viewer where you can look at these images and so forth. So all of that is computer science, and the people and students who work on that mostly have a computer science background or a bioengineering background, or sometimes you have MDs who are really, really interested and spend a lot of time in computer science. So what's the state of the art? So the data sets usually are rather small to train these systems. So as we learned, if you train an AI or machine learning system, you have to show them a lot of examples. On the x-axis, you see the years, and then the y-axis, the size of these data sets. When we coined the term computational pathology over a decade ago, we started with one of these slides. And these days, the top systems from Google, for example, who has a large team in pathology, work on 500 to 1,000 of these very, very large images. The problem is that the data sets at that size are still very well curated. So you only have the well-processed images and the nice ones, and all the difficult ones are removed. And in practice, that's really like training a self-driving car on an empty parking lot. It will work perfectly fine. It will never make a mistake. All your metrics will be great. It will be precise and accurate and so forth. But as soon as you hit reality, it will fail drastically, because reality is messy, it's diverse, it's surprising. And the same trouble a self-driving car would have in the middle of New York or San Francisco, the AI systems in pathology have if they see slides from hospitals all over the world. So to overcome that, it takes 4 large areas. The first one is machine learning. It's new algorithms, new methods to train these AIs. The second is data, data at scale, data that reflects reality. The third one is domain expertise of computer scientists and MDs. And the last one is computation at scale. One of the big problems in practice is that most of the time when these systems are trained, as you see on the left, you have to have doctors who actually manually annotate the slides. So they have to paint on it. In this case, it's a prostate cancer biopsy, and these are graded with something called Gleason grade. That's a Gleason grade 3 cancer, and they have to paint on the cancerous cells. And then you can take these painted areas and everything that's not painted and train a system for cancer and non-cancer. The same way we saw at the beginning how we train a system for outdoor and indoor images. The problem is you can only do that on a few hundred slides and takes a lot of time. On the right, we came up with a system where we directly take the binary label from the report. So from the reports, we learn if an image is cancerous or non-cancerous. And the problem is these can be very small cancers. So what you see on the left is elongated structures. That's tissue from the prostate, from a needle biopsy. In a prostate needle biopsy, so 12 needles are used to take biopsies to look for cancer. And then on the zoom-in inlays, you see that the cancerous lesion on the right, the cancer cells, can be very, very small. So it's really like looking for a needle in a haystack. And until recently, nobody came up with a system that was able to find cancer in these large images effectively. We built a system to do so, which was published in 2019 in Nature Medicine. And it works as follows. So on a very high level, you have a stack of slides from which you know there's no cancer. So it's normal tissue, healthy tissue. On the other hand, you have a stack of slides for which you know there is cancer. And what the system does is it compares these images to each other over and over and over again to learn what the difference is. And the difference are not the variabilities of cells and vessels and tissue, and it's not also the bubbles and paint and all the processing problems. The difference is the cancer morphology. So how does cancer look like? How the cells look like? Very briefly, for the ones who are interested, practically what we do is we tile these images in tens of thousands of small pictures, which we then stream through a convolutional neural network in the middle. Then you end up with a ranking of these patches. And the hypothesis is if it's a cancerous slide, at least one of them is cancerous, which you then can use to calculate an error to the clinical report and then back propagate it. And if you do that over and over and over again, the system starts to learn how to do that. On new slides, you then also aggregate the information over the whole slide with a few tricks, and you end up with a classification of such a slide. What you see here is on the x-axis the size of systems when we train these. Each of the dots is a different model, and on the y-axis the error. And if you are at the scale of these systems from Google, for example, you still have high error rates. But if you start to train these models with 6, 7, 8,000 slides, which has never been done before, the AI starts to learn by itself how cancer looks like. We then tested that on prostate cancer, skin, and breast cancer, and it works very well. So the images, the plots show you a metric that shows near perfect performance of these systems. And if you use some mathematical gymnastic, you can use these also to actually paint on the images and show the doctor where the cancer is, how it looks like, how big it is, and so forth. To test the system and see if it really works across all kinds of communities and ethnicities, we tested it on 12,700 patients out of 800 hospitals from over 42 countries worldwide. So in these cases, the slides actually were produced in China and India and Europe, all over the US, and then sent to Memorial Sloan Kettering in New York for scanning. And the system performs very well. So the state-of-the-art systems have no drop in performance. So like a human, that's the first system that actually can find cancer even if the slides are brighter or darker, or in France, they still use saffron to stain some of these slides and so forth. So here we have a system that's truly clinic grade, so that could work in the clinic. And we were very humbled in that system that the FDA, so the Food and Drug Agency, which is responsible for regulating AI and medical devices, gave us a breakthrough designation, which is the first breakthrough designation for an artificial intelligence, not only in pathology, but in all of oncology, so cancer research. So the hope is that very soon you will have these systems in clinical practice. They can help doctors to be faster and only look at the difficult cases. And more importantly, they can also help the patients to be treated better. So what you see here in gray are the sensitivity of pathologists. So we had pathologists all over the country look at 300 of these slides and try to find the cancer. And as you can see in light gray, if the cancer is rather small, so less than 1 millimeter, for example, they miss a lot. So even half of them. So these are community pathologists who are under enormous stress, and they miss a lot of cancer. And then 5 weeks later, so that's a washout period where you usually forget the original slides, they looked at the slides again, but this time together with the AI, what you see in black is then the increase in sensitivity for these pathologists. So they now find the cancer with the help of the AI. So the human with the AI is significantly better than the human alone. And for the patient, that means, of course, increased detection rates, better treatment, and hopefully also better outcome. It's also rather cheap. Not everybody can afford to go to these ivory towers like Dana-Farber or Memorial Sloan Kettering or Mount Sinai, but you can deploy the AI through the cloud everywhere in the world or somewhere in the countryside, and then patients there would get nearly the same performance or diagnostic as they would get in one of these top-notch cancer centers. You can use it for quality assurance, so to really find all the cases so nothing is missed. And things I didn't talk about today is for detection of genomics, for example, in other areas. So in summary, we can say today, in contrary to the Terminator images we started with, today patients are dying not because of artificial intelligence, but because of the lack of artificial intelligence. So all that is only possible because of the fabulous teams we have at Mount Sinai, Sloan Kettering, and Page, and all the collaborators all over the country. And at Mount Sinai, the vision is that what we build in pathology, we're gonna reproduce in all other areas of the hospital, like genomics, ophthalmology, IBD, dermatology, and really build a fabric of AI systems that all work together and support the nurses, the physicians, and also the administrators to the single goal to get better outcome for these patients. So this is a very exciting area, of course, as you can see, and we are still just at the beginning. So if you imagine healthcare in a few years, it will be completely changed through AI. It will be much more interesting for most of these disciplines to be a doctor. You do not have to do the repetitive, boring tasks, but you have all these additional information that help you to treat the patients. Okay, I stop here and would love to go into Q&A.
Danke